rigid rotor model for diatomic molecules. Let us assume carbon monoxide is a diatomic molecule. Carbon mass, atomic mass of the carbon is 12, atomic mass of the oxygen is 16. Clearly the carbon was shown with red color and the oxygen was shown with blue color. Okay. And this carbon monoxide molecule is a diatomic molecule. Now, the center of gravity of this molecule, okay, this is where it will be located near to oxygen, because the atomic mass of the oxygen is 16, atomic mass of the carbon is 12. That's what the center of gravity of the molecule was located near to the oxygen. Okay, this is what the center of the gravity. We have indicated with the C. Already we know the moment of inertia, and based on the moment of inertia, we have even classified the molecules to various types. Now, based on the moment of inertia and at center of gravity, the momentum, that is mass and radius, that is the at C, that is at center of gravity, what will happen? M1 and R1. The radius of the M1 atom is R1, that we are indicated with red color. You see that up to this is the radius of the M1. Up to this is the radius of oxygen, R2. Okay. Now, at this C point, at this center of gravity, this is what we assume, that the M1 R1 equal to M2 R2. That is what the standard thing. Okay. M1 R1 equal to M2 R2 at center of gravity. And now the radius of the CO molecule, that is carbon and oxygen, is R. And moreover, this R is equivalent to R1 plus R2. R is equivalent to R1 plus R2. Okay. You remember these two conditions. One is R1, R is equal to R1 plus R2, and M1 R1 equal to M2 R2. Okay. We are assuming that mass of the carbon is M1 and mass of the oxygen is M2, and even we have denoted that the atomic mass is 12.0001 and the atomic mass of the oxygen is 15.9994. This is what a rigid rotor model. And what is the difference between this vibrational spectroscopy and rotational spectroscopy? There, this vibrational energy, this simple harmonic motion or simple harmonic vibrator, we are considering it as a potential energy. In this case, it is a kinetic energy. You keep in mind, this is kinetic energy. In vibrational spectroscopy and for determination of K, we are considering it is a potential energy. Okay, that is the major difference between these both spectroscopies. Now, as we have discussed, at center of gravity, what happens? M1 R1 is equal to M2 R2. And now the moment of inertia of the entire molecule, that is I equal to M1 R1 square plus M2 R2 square. We know the formula for moment of inertia. Moment of inertia equal to mr square. Now, since we are having two atoms here, moment of inertia of the first atom, the moment of inertia of the second atom, if you add, that will be the entire moment of inertia of the molecule, that is carbon monoxide or molecule. Let us assume it is a carbon monoxide. I is equal to M1 R1 square plus M2 R2 square. Let us assume this is equation 1 and this is equation 2. If you combine these both equations, what will happen? Just let us. And one more thing is, instead of M1 R1, you can substitute M2 R2, or instead of M2 R2, you can substitute M1 R1. Just we are submitting, we are substituting that, and we are getting a simple equation, that is I is equal to R1 R2 into M1 plus M2. This is equation 3. You understand what is M1, the atomic mass of the carbon, M2 is atomic mass of the oxygen. Now, M1 R1 equal to M2 R2. At which place? at the center of the gravity or at the center of the mass. Okay. So now the moment of inertia of the molecule is I is equal to m1 r1 square plus m2 r2 square. Okay. So now I is equal to, we are substituting instead of m2 r2, we are submitting m1 r1. That's what, and m1 r1, vice versa, we are substituting, and we are getting this equation. And if you take r1 r2 as a common, r1 r2 into m1 plus m2, this is equation 3. Okay, 1 2 3 equations. And one more thing is R is equal to R1 plus R2. R is equal to R1 plus R2. So now, based on this fourth equation and based on the first equation, first 1 and 2 we are getting 3, and now 1 and 4 we are getting fifth equation. That's, let us, R is equal to R1 plus R2. R2 is equal to R minus R1. R1 is equal to R minus R2. Okay. This is a simply, we can substitute if we want to find out R1. What is the thing? Total radius minus R2. If you want to find out R2, R minus R1. This both equation you substitute in equation 1. We are substituting this R is equal to R1 equal to R minus R2. R2 is equal to R minus R1. Both the equations simultaneously we are substituting in equation 1. Let us, instead of R1, R minus R2 we are substituting. Instead of R2 we are submitting R minus R1. So now we are simplifying these equations both. We are just multiplying and just we are sending this M1 R2 term that side, right side, and we are taking R2 common, and we are going to find out R2 here. Now what will happen? M1 R by M1 plus M2. What is the now radius of the second molecule R2 is equal to M1 R by M1 plus M2. Similarly, the second thing, you see that M1 R1 equal to M1 M2 minus M2 into R minus R1. Where this R minus R1 has come, instead of R2, I am sending this R1 that side. R minus R1. It becomes R minus R1. I am substituting in equation 1. And both the terms, R1 term I am deriving and R2 term I have derived. Okay. Both the terms we have derived. Now, this 5, equation 5, we are going to substitute in equation 3. What is equation 3? This is the equation 3. Okay. I is equal to R1 R2 into M1 plus M2. From equation 5, what we know? R1 is equal to M2 R by M1 plus M2, and R1 is equal to M2 R by M1 plus M2. Okay. So now if you substituting these two terms in this equation, what we get, just this is the R1 and R2. Directly if you substitute this R1, R2 values in the third equation, what we get? I is equal to M2R by M1 plus M2, M1R by M1 plus M2 into M1 plus M2. Okay. So now this M1 plus M2 cancelled, and M1, M2 R square. Okay. This is M1, M2 R square divided by M1 plus M2. Now, instead of writing this I is equal to M1, M2 by M1 plus M2 into R square, I am substituting this M1, M2 by M1 plus 2 with mu. Now, I is equal to mu R square. Now, mu is equal to what? M1 by M1 plus M2. We have used this equation already in calculation of force constant. In vibrational spectroscopy, determination of force constant, we have discussed about this mu value. What is this mu? Reduced mass. Mu is equal to reduced mass, that is M1, M2 by M1 plus M2. This is what the derivation for mu. Okay, reduced mass derivation. How we are deriving? Just we are assuming the diatomic molecule, that is carbon monoxide, and we are applying the rigid rotor model to that, and at center of gravity we are assuming that M1 R1 is equal to M2 R2, and we know that R is equal to R1 plus R2, and total moment of inertia equal to I is equal to m1r1 square plus m2r2 square. And now with these three equations, finally what equation we are getting? I is equal to mu r square. Mu is equal to m1 m2 by m1 plus m2 into that's it, m1 plus m2. Okay, this is what the reduced mass. Always this reduced mass we are converting into kgs. Mostly atomic mass unit, the mass of the atoms will be in atomic mass unit. One atomic mass unit equal to 1.66 into 10 power minus 27 kg. We will be multiplying the atomic mass units, whatever we are getting from this mu, with 1.66 into 10 power minus 27 kg. That means reduced mass you will be getting in kgs. So now the same thing, just we have written here clearly how the mu will come. I is equal to mu r square. Okay, now this is mu and the same mu, and so now as we have discussed, this is a kinetic energy. In classical expression, the energy of rotation is kinetic energy. Vibration is potential energy. Now, what is the formula for kinetic energy? Of mv square, we know already, okay? It is an it is instead of m, we are taking I, that is moment of inertia, and the omega, angular velocity, that is w. So now of mv square, it is looking like of mv square. You see that this is the energy of the molecule of mv square. It is a kinetic energy. Okay, now we are having already the relation between L, it is an angular momentum, and I and omega. L is equal to I omega. Now, instead of writing L square, I have to keep one I in denominator because only one I is there in numerator. Now, I'm writing the term L square. That's what 1 by 2 is there. Instead of, I'm writing that L square. If you are writing L square in denominator, I have to keep I because only one I is there in the equation. Now, L square we are keeping. L square means I square omega square. Now, in denominator, I am keeping one I. This is what the energy of the rotational thing, rotational energy level. And now, what is this L? L is equal to angular momentum, and L square is an operator. Like in Schrodinger equation, we are getting Hamiltonian operator here. This is also an operator. What is that operator? L square is equal to h square by 2 pi square whole square into j plus 1. What is this j? J is equal to rotational quantum number. Instead of writing L square, we can keep this value in this equation. That is energy equal to 1 by 2I into h square by 4 pi square into j plus 1. Okay. Instead of writing 4 and 2, 8, directly we can write energy of the rotational level Ej equal to h square by 8 pi square I into j plus 1. Normally, the energy of the rotational level we are expressing in wave number. In order to expressing this energy in wave number, we are dividing this equation with Hc. If we are dividing this equation with Hc, what happens? Hh will get cancelled. H by 8 pi square Ic will be remained. Okay, that is what the energy level in wave number. And H by 8 pi square Ic is the B. Instead of writing this term here, I am keeping B. B is a rotational constant. What is the B? B equal to rotational constant. Now, if you want to find out the J, we have to find out the B first. If you know the B, we can calculate the J. Okay. The energy of the rotational energy level can be quantized with this equation Ej equal to h square by 8 pi square I into j plus 1. And instead of expressing this energy in joules or other, we are expressing in wave number. In order to express the wave number, we are dividing this equation with hc. Okay, and Ej equal to B into J plus 1. Now B is equal to H by 8 pi square IC. Okay, and this is what the derivation for energy for a rotational energy level. So now we will find out the energy of J0, J1, J2, J3 and J4. Okay, let us assume the same thing. We will take, this is one energy level, that is second energy level J2 or J1. Okay, and this is J2 and J3. We can keep one more here. Okay, now what will be the difference between this and this? Here if you see 0 and 2B, we are expressing energy in B with respect to B term. Okay, we know what is B already. B is equal to H by 8 pi square into I by C. Now this is 6B. Why this B, how this 2B, 6B and 10B is coming? If you keep J is equal to 0, what happens? Entire energy will be 0. If J is equal to 1, what will happen? 2B. If J is equal to 2, 6. If J is equal to 3, what will happen? 12. See that it is very simple. We are expressing the energy of this each rotational levels with respect to B term. And now 0, 1, 2, 3, 4. 4 plus 4 into 4 plus 1. How much? 20. 20B. Now we have to calculate the J value for carbon monoxide molecule. Okay. So what is the del J? The difference between 1 and 0, that is 2B. This is first rotational transition difference. Okay, del J equal to plus 1. If suppose third and second, what is the difference? 4B. What is the difference between this? 6. What is the difference between 8? Similarly, you can keep, so what is the value of this? J equal to, capital J equal to 0. And second one, what is that? J is equal to, this is J is equal to 0, this is J is equal to 1, this is J is equal to 2, and this is J is equal to 3, and this is J is equal to 4, and this is J is equal to 5. We will write one more and what nothing will, yes, this is J. Now we have to change the value, just J is equal to 1 and J is equal to 2, J is equal to 3, J is equal to 4, J is equal to 5. Okay. Now 5 into 630, just you see that. What is the difference between the this 20B and they may ask us to find out the J value for carbon monoxide. Okay, J value for carbon monoxide. Now we know the formula just and we know H value and we know I value, that is mu R square, and we know the radius of the molecule that they will provide in formula just, and we know the C value and we will find out the B. And if we know the B, what we can find out the difference between J1 and J0, the difference between J2 and J1, the difference between J3 and J2. Just you see that this is a 30B. Okay, this is what the second term, the calculation of the J value for diatomic molecules. Okay, this is for diatomic molecules, not for polyatomic molecules. The polyatomic molecules, that is a different thing. Okay, for carbon monoxide, for HCl, for NO, SO, O2. Okay, this type of things we can calculate J. The advantage of this thing is we can find out the bond length. You see that here you have remembered or not, if you know the, we can find out the bond length. You see that R is equal to R1. If you know the atom information, we can find out the bond length of the molecule. Just you see that. That is what the advantage of this microwave spectroscopy. We can find out exclusively, and no other spectroscopy will give the information of bond length. Only the rotational spectroscopy will give us. Okay, you keep in mind, this is the one of the important application of microwave spectroscopy. We can find out bond length from rotational spectroscopy. From vibrational spectroscopy, what we can find? We can find bond, yes, whether it is stretching or bending. This is how it was. Qualitatively we can tell. We cannot quantitatively tell the bond length in the vibrational spectroscopy. It is a bond angles, how it will influence that. That we can tell, but we cannot tell from vibrational spectroscopy, this is the bond angle. Okay. From the microwave spectroscopy, we can calculate, we can tell, this is the bond length. Now R is the bond length. Okay, what is the small r? Here in green color, you see that small r equal to R1 plus R2. Okay, that is the green color. This is the bond length from this mid to this mid. Okay, and R1 is this one, R2 is this one. This is carbon and this is oxygen. Okay, this is what the expression of J for rotational energy levels. Okay, this is what the expression of J for rotational energy level.